Okay, welcome everybody. Yeah, if you have questions, just let me know. The plan for today is basically I will give a bit of introduction to pharmacokinetics, basically how pharmacokinetics data is looking and how this is normally reported if you look at clinical studies and look at publications. And this gives you basically the background information for the data curation and for reading your publication about lisinopril. The main idea is today to give this basic introduction. In the end, we will do some organizational things, and then within the week, I would provide a set of publications which we have to work on, and then everybody would select 1, 2 publications and start reading them, working on the data curation and so on. But I will provide more information about that. So today is more like the theoretical background that you are able to understand, okay, what is important in this papers and what data do we require to build the model. Okay, please feel free to ask questions, and often it helps a lot to have like some discussion about the things to make stuff clearer. Yeah, otherwise like I mentioned, I'm recording that, and it's more like, okay, if you want to rewatch the lecture, or if you can't participate on some days, you can rewatch the videos. Okay. Let's get started. Yeah, quick reminder why we're doing all of that. The basic idea is really in a collaborative project with students to develop a physiological-based pharmacokinetic model of the ACE inhibitor lisinopril. So we finished most of ramipril, and here in this course we work on lisinopril. It could be that we extend this all to the theoretics. My first look on lisinopril showed like, okay, this is pretty straightforward to do and it's probably not too complicated. So perhaps we can even extend a bit the scope if the data curation works well, and yeah, I'm pretty optimistic that this will work. So what is pharmacokinetics? I think the main idea about pharmacokinetics is studying time courses of drugs or medications. And normally you give the medication to treat a certain disease or treat certain symptoms. And what you want is, if you apply this multiple times, that you get in the so-called therapeutic window. It's mean like you want the right plasma concentrations over time, so that it has basically the desired effect, the drug or medication, and you don't want to be too low, which would be ineffective, and you don't want to be too high, because often this results then in adverse effects. Interestingly, if you give a drug multiple times, you see multiple of these peaks I showed in the first in the introduction. So basically, if you give the drug, normally it appears in the plasma, it goes up, and then it goes down again over the time. And of course, if you now take your tablets like every 24 hours, you get multiple of these peaks. And if your drug is not removed completely from the system in 24 hours, then you get some accumulation until you get some certain steady state concentrations. And that's also like I think this understanding these curves and seeing these curves is really informative, because it tells you a lot of things what you should and shouldn't do. Like, for instance, like often people, when they forget to take their medication, they take 2 tablets on the next day and things like that. And so this is definitely not a good thing to do, because you get just totally different plasma peak concentrations. So yeah, that's, I would say, the whole idea of drug therapy, and of course this therapeutic window can be very different for every individual. So what is pharmacokinetics? In summary, it's a quantitative study of drug movement in, through, and out of the body. So you're interested in, if you put substances in your body, how they distribute and how they're eliminated, and yeah, what the concentrations on different sites in your body are. Like often the main interest is the site of action. It's basically the place where the drug should actually be and have its desired effect. But often you're also interested in different places, like in different organs and so on, because you can have certain side effects or and so on. Why is it important to understand pharmacokinetic properties? It has a lot of reasons. One is it's important to determine the route of administrations. So depending on your drug properties and pharmacokinetic properties, you have to do a certain application. Like for instance, if the drug is strongly cleared by the stomach, which is often like you have like medications which are very unstable at low pH and so on, then often oral administration is not really working because basically nothing is going into the intestine and the systemic circulation. So understanding these properties of the drugs are important to determine how you should apply it and also how often you should apply it. Like for instance, if you have medications which has a very short half-life and it's removed very fast from the body in a few hours, then it's very difficult to get like pretty stable concentrations over time. And so often you give this via some muscular injection or so on, or via tablets which are slowly releasing the substance so that you get a more constant drug concentration. Also, it's important to understand the onset of action. So basically, when these peaks appear and when they are going down, they're telling you also when the pharmacodynamic effect will be. For instance, for the caffeine, like you expect the most of the effect to appear around 1 or 2 hours because you basically have the maximal plasma concentration. And it tells you also a lot about the duration of action. Like for instance, here with the caffeine, basically from these curves, you can already see, okay, this normally would work around 8 hours and so on. And then I probably have to drink more coffee and so on if I want more of the desired effect. How is this pharmacokinetics studied? I would say the biggest thing is this ADME. It's short for administration, distribution, metabolization, and elimination, or absorption or administration. And it tells you basically, okay, how the drug is going into the system, how it's distributed, how it's metabolized, and in the end, how it's eliminated. I showed this last week, but basically, if you put this different processes in computational models, you are able to understand, okay, how these peaks appear and how these peaks disappear. So in the end, pharmacokinetics is basically, okay, I would say the study of this time courses of the drug in different compartments. What you do now in pharmacokinetics is that you can calculate certain parameters from these curves. So you're mainly interested in, okay, how is this going up and going down over the time? And you can use this curve shape to calculate certain parameters. And this gives you basically a parameter to evaluate how this drug is working. Things you often do is like something which is called Cmax, and it's the maximal concentration. You have things like Tmax, which is the time of maximal concentration, area under the curve, which is basically the area under the concentration curve, often the plasma concentration curve. You have like elimination rates. This is basically gives you the rate constant on how fast this is eliminated. And you have things like half-lives. Okay, how long does it take until the concentration goes down to half of the maximal concentrations and so on. You also have other things, which is called volume of distribution, and this is this gives you basically it's a bit of a complicated concept, but it gives you basically a virtual compartment in which the drug would distribute. It is basically, you can imagine if you give a certain dose and it you see a certain plasma concentration, then you can calculate basically a virtual compartment which gives you a certain size. And okay, I will talk a bit more about that, but this is basically also a concept which is very often used. And then you have something which is called clearance, and this gives can basically be calculated from the dose you gave via the area under the curve of this curve. Okay, how is the elimination rate calculated? This is basically done on a log scale. So you take this concentration time dependency, and you take the logarithm, and then you use this basically this terminal phase of elimination, which is often a straight line, and from the straight line via a curve fit you can estimate the elimination rate. Okay. Here also interesting things is that you have very different curves depending on the oral and the intravenous application. So if you give something intravenous, it's very fast in the system. So you basically inject it, and within a few seconds, up to a minute, you reach the maximal concentrations in the blood, and then it goes down very fast. Why is this looking for different for the oral administration? It's basically it's because it takes some time for the heparin to dissolve, or for the so if you take a solution to go through the stomach. So basically, you have a stomach passage. It takes some time until this can appear in the intestine, until it can be absorbed, and normally you have this lag time of half an hour until 1 or 2 hours, depending on many things, like depending on if you have eaten, if you take a lot of food, it takes often longer for the drugs to appear in the system, or depending on the site of absorption. So you can basically have a very long intestine, and certain drugs can be more absorbed in the duodenum, others in the ileum and jelenum, and so on and so on. So depending on where this absorption is actually taking place in your intestine, it can take longer. So the further you're down in the intestine and have absorption, the larger lag times you basically have. So a lot is just understanding, okay, what are the physiological effects which can change these curves? And to quantify what is the change in this curve, you can calculate these parameters. Okay. Okay, like I said, if you have questions, just ask. Otherwise, okay. I think that the important thing is just to introduce this concept, and most of the time in your papers, you will basically find some table of this pharmacokinetic parameters and some data about this time concentration curves. And to have a basic understanding how this is calculated from these curves helps you basically to bring the parameters together with this curve shapes. Okay. So I will show basically an example of how such data can be reported, and this is a made-up substance which is called pretenderlone. And yeah, we basically follow simple clinical trials where we have 5 subjects, and every of these 5 subjects received 2 different application forms. Once they got 50 milligrams of oral pretenderlone, and the other time they got a 2 milligram bolus injection of the drug. And so we are now interested in, okay, how could like data look like for these 5 subjects, and what is the difference? So often what you find is tables of the actual time courses of the drug. In this case, okay, this is for the 5 subjects, the plasma concentrations after the 50 milligram oral dose. And so what you get, normally you get a certain sampling interval at certain time points, often non-equidistant. You take some plasma sample, and then you determine the concentration of your drug, here the concentration of pretenderlone, using mass spec or different methods for quantification. And then you put in the end this data into a table, and have for every subject basically this measurements. You can then calculate certain things like the means, standard deviation, coefficients of variation, and often like in this pharmacokinetic fields, they also use the geometric mean for calculation. You can then plot the data from this table, and then you see such time curves basically for every of these 5 subjects. You see, okay, at the beginning we have at 1 minute very slow sampling, a very low concentration, and then already at 5 minutes we basically have the maximal concentrations of this drug. But you have but it takes a bit of time for the drug to get up in the beginning. It's basically how these injection protocols are working. So it's mainly, okay, you could ask, okay, basically if I inject this in 1 second, why don't I see like very high peaks after 1 or 2 seconds? Because the main thing is that the sampling is always done. You inject in one arm and then you sample in the other arm. And this is to avoid contamination of the basically of the sampling site. You can imagine if you basically sample from the same site where you injected, you will get like a lot of errors and problems because you have a very high local concentration. But this is not yet the actual plasma concentration, but it's a concentration in the venules and arterioles and so on. So in the small vessels which you have at the injection site. And so it takes some time for the blood, okay, from your arm when you inject it to reach the systemic circulation. It has to be distributed to the body, and then you sample on the other time. And this takes some time, like this distribution phase and so on. And that's why, okay, normally after 2 or 3 minutes, you see the maximum concentrations, but not after the first 10 seconds. Okay, this is how the data looks. Certain things which we can observe. I would say the first thing is that the intra-individual variability of this pretenderlone example is very low. And this means really like all the curves look the same. You almost don't have any errors between the different sites. And this is, it's a good thing, but often this is very drug dependent if you have like a large variability or not. But in this case, the differences are very low. And so basically everybody is like very close at the mean curves over time. Also this basically the rate of disappearance seems to be very similar. It's not only that we have high similar peak concentrations, but also these rates of disappearance are very similar. It's not like that one subject is like going down in 6 hours or the other in 36 hours. Also this there seems to be like not much variability in this elimination rate. Okay, and so often you don't see these tables in publications, but you see this actual data. Unfortunately, often you don't see the individual data, but you only see the means and the standard deviation or standard errors plotted on such pharmacokinetic data sets. How this is appearing then, this would be more like a publication plot. You can see basically it's only the mean and the standard deviation here, or mean or standard standard deviation here is plotted. Often they use standard error because standard errors are smaller than standard deviation, then the error looks smaller, and they often plot it on logarithmic scales. And this is also what you have to look out. If you read the papers, okay, man, what was actually plotted? So what are the concentrations in this? What are the units? And what was plotted? In this case, it's really pretenderlone in nanograms per milliliter plasma. So what was the tissue? You could sample in plasma or saliva, saliva or serum and so on. So it's important. Where was it sampled? How is this plotted? What is the actual unit? What are the time units? Is this all equidistant? And what was actually plotted? Is this mean? Is it geometric mean? Is it ST? Is it SE? So it's you have to look at basically like be a inspector, like being a detective, and figuring out, okay, what do I actually see here? Because you have to understand, okay, what is it actually what I see? Because you have to put it or map it somehow on the model and put the data together with the other data from the other students. And I would say this is one of the biggest challenges to understand, okay, often what is plotted, because information is not all provided in the figure legend, but it's somewhere hidden in the text and in the methods and so on. So you have to be a bit of detective work to understand. Like for instance, here also, like you would never know this were 5 subjects. Or here you would know it. Okay, the n equals 5, but often this is not given, and then you have to look in the publication how many subjects were in this group in which here oral pretenderlone was measured. Okay, this was basically the intravenous part. It's like so basically very fast. We see the this was when I said a lot of nonsense, sorry, you have to correct me. Like, okay, the main nonsense was, okay, all these things about intravenous is correct, but here it's more like, okay, we see this was the oral dose. In the intravenous, it's basically, okay, you would see higher peak concentrations, and okay, so most of the things I said is correct, but okay, the intravenous thing would be even even higher here after the first minutes. So okay, sorry, this was a bit nonsense. Okay, just correct me there. Yeah. Okay. Okay, so here the question is, okay, where's this upcoming flank coming from, and where's the downwards flank coming from here in this example? And it's basically it's a combination of drug absorption and drug elimination. And so in the beginning, you give the drug, in this case orally, and you have a lot of absorption, and the absorption process is putting the drug into the plasma. And this results in an increase of the plasma concentration. And in the beginning, okay, you don't have much elimination because, the absorption process is basically dominating. And so you have a bit of elimination, but the elimination flux is much lower than the absorption flux. And so overall, then the concentration is going up. This is always a mass balance. Okay, which processes contribute to your plasma concentration and which processes eliminated. And so if the contributors are larger than the eliminators, then you have an increase in concentration and vice versa. So at the beginning here in the absorption phase, the absorption is greater than the elimination. Then at the peak points, it's basically you have the absorption is equal to the elimination, and then in the elimination phase, the elimination is dominating. But you still have like absorption in this phase. It's more like the elimination is bigger than the absorption. And then from this curve, you can calculate this pharmacokinetic parameters. In this simple example, you can calculate two parameters: is maximal concentration, and it's time of maximal concentration. So you would look for the 5 subjects in here, can calculate these values, and can of course also do things like mean, standard deviations, and so on. And this is then often the parameters you find in the publications. It's for a certain group. Here 5. The mean and the standard deviation of parameters which you calculated from this curve. And often these curves are not even shown. So it's more like you just see the parameters and basically all this thing. Oh man, they gave the drug, they sampled a lot, they got the time course, they calculated pharmacokinetic parameters. This is basically just implicit. By seeing such parameters, you know that they did it and they describe it somewhere in the method. But often like there's a lot going on, but yet they're not showing all the data. They're basically just showing a parameter which is calculated in the end. For the elimination, for this elimination rate, you like I said, you do normally the logarithm here, and then you calculate do an interpolation and calculate the elimination rate. You can also do this via just calculating the difference in concentration over time, and can get from that an elimination rate. But this is basically just a local estimate. Overall, you're more interested in, okay, what is the overall elimination rate? And here you can see, if you do the local calculation via 2 time points, yeah, this looks very similar for the different subjects. If you would use different time points, or you would get different values. So what in reality you're doing is you're using all the time points which are in the elimination phase and make a curve fit, and then calculate from this curve fit this elimination rate parameter. Okay, but this is
Yes.
Yeah.
Sorry for interrupting. What does KH-1 measure?
It's basically it's how fast is the concentration disappearing from the plasma. That's basically this rate of disappearance.
Okay, thank you.
So and it makes a lot of sense. Like if you remember this is like a bit of the inverse of the half-life. If you do ln2 times this rate, through this rate, it's basically the half-life. So this is somehow reciprocal to the half-life. So the faster the rate of the disappearance, the slower the faster the rate, the slower is the half-life. This makes okay, it makes more sense. Like, or basically, it's basically this how fast is this going down? So K is higher if this is going down faster and faster, and of course then also your half-lives are getting smaller and smaller. And if you have very slow elimination rates, and the curve would be here somewhere, then you would have like very long half-lives, and it would take 36 hours for the drug to go to half concentration.
Is there any like ideal like curve form to this? Like I'm aware that if this goes super fast, then
I don't know. It depends on
that, right?
It depends on what you want. Like I couldn't.
Right.
Like, insulin is a good example for that, and you have slow acting and fast acting insulins. And then so basically, if you inject insulin via the pen with a fast acting insulin, basically you have like half-lives of a few hours, 2 or 3 hours, and that's what you basically want. You know, okay, I eat a high carbohydrate meal, and I will get a peak in glucose. So I want just for this next 2 hours, I want a peak in insulin, and then I want the insulin to be away. So you would use like the a fast-acting insulin, which has a very slow half-life, a fast elimination rate. On the other hand, you want if you want to control more over the whole day, you would use like a long-acting insulin, or an insulin which you inject more in the muscle or in a depot, and then you would have for the same drug a much slower half-life. And what I would say, like, ideal is difficult to say. What you normally want is pretty constant plasma concentrations, so that you are in this therapeutic window. And so it's let's say it's ideal if it's around 24 hours, like your half-life. Because then you don't only have to take the tablet every once per day, and you have pretty stable rates. But often you have like very long like it depends on the drug and the elimination process of the body. So often you can't do much about it. If things are too slow, you can put it in special tablets and coat it, and then you get a slower absorption and can slow the process via that. But otherwise, you don't have much manipulation here.
Okay,
and yeah, but it's difficult to say. It depends really on what you want. If you want fast action and want the thing only for a short time in your system, you would use something. You want something with a slow half-life. If you want constant concentration over days, you want something which is around 24 hours. But some drugs have Marcomar, which is a blood thinner, and so on. They basically have half-lives of 7 days or so, and then so it's just craziness, like, because you get like accumulation over weeks and months, and it's really hard to concentrate your plasma concentrations with things like that. Here with the drug formulation, exactly. This is basically where you have a bit of manipulation possibilities. So basically, if you have a fast-releasing tablet, most of the substance is going out of the tablet and in the stomach or in the intestine very fast, and then you have a lot of things in the plasma, and then the elimination is very slow. On the other hand, if you have a fast release tablet, then basically nothing is in the bloodstream after like a few hours, because everything is already released, and you will get things like that. You get a pretty fast release in 1 or 2 hours, and then afterwards it's basically elimination, which is putting the whole thing down. In contrast, if you have a more like slow releasing tablet, then you can basically see this. It's basically releasing in this initial phase, like in the first 2 or 3 hours, but then you still have like a lot of substance left in the tablet, which is going up in the later hours, and then it looks like you have a slower elimination rate, but in reality, it's more like your substance is still appearing after a very long time, and so this whole thing is smoothened out. And this is, for instance, where I have like as a drug company also like possibilities to manipulate this rates. Sorry, before I mix up the oral and intravenous applications, but okay, for the intravenous, you basically see, okay, you have very high plasma concentrations already like at the beginning. And so like I said, like after 1 minute, 2 minutes, you have the maximum concentrations. Like for the subject 1, you see basically, okay, you have after 5 minutes or something like that, you have some of the maximum concentration, but it takes it takes 1-2 minutes until you get to the maximum. But overall, the curve looks it looks mainly different in this initial phase, and this is the absorption phase. And because you don't have really absorption in the intravenous case, the elimination phase is most of the time looking very similar for the drug. So I would say there's also a takeaway, like it doesn't really matter how you get this drug into the plasma via which route. In the end, the elimination is very similar. Just the absorption or like the administration basically decides, okay, how fast are things appearing in the system and for how long. Okay. Not sure if I think, okay, perfect. Yeah, if I'm freezing, you have to tell me, like probably the computer is dying in a minute. Okay, but here, yeah, for the intravenous application, okay, things look very similar. You have basically plasma concentration curves for the different substances. You can do mean, standard deviation, and then you can calculate also like elimination rates and so on and so on. Yeah, and like I said in the beginning, you have like a distribution phase, and normally you calculate the elimination rate in this elimination phase. So this beginning is yeah, the drug has to just distribute through your system and equilibrate with the different tissues. Okay, depends if the things can be taken up by the tissues and so on. But you have this equilibration phase, and then you most of the time have a mono exponential decay of the drug. But this also depends on the substance. For instance, alcohol is an interesting exception, which is basically not going via this mono exponential decay, but it's a first order decay. And it's basically because your alcohol dehydrogenase, it's basically completely saturated with alcohol because it has like certain kinetic properties. And so for alcohol, this curve would look very different than for other substances. But as a rule of thumb, if you have to guess, you would say there's a mono exponential decay, and this would look very similar to such a curve. And if you know the half-life, you can also like already say, okay, after which time is this going down, and what would be a good dosing protocol for the substance. And then similar, you can calculate the elimination rate and the half-life on that. Here to the half-life, I have a few examples. That's also back to the question. You can see there's big differences, and often you can't really control that. That depends a lot on the metabolism and elimination processes you have in your body. And so this is a large difference between certain cancer drugs and acetaminophen, which is around 2 hours, and things like cannabis or so, where the THC and so on, it's normally 2 to 5 days half-life. And that's also like, okay, if people smoke a joint, they feel pretty good on the next day, but okay, man, they're still let's say, they're still half stoned for 2 to 5 days. That's just some examples. Other things, it can be super long, and it depends a lot on special things, like there are really like some freak things, like certain things, or certain kinds of ecstasy. It's basically just stored in your fat tissue, and then it just can come out after like a month and years, and you get flashbacks and so on. So there's certain things which is it's just really strange, and it's not this classical, it disappears, but it disappears, but it's just stored in your fat tissue, and at some point it can be released from your fat tissues even months and years after you took certain things. There's also problems with mercury accumulation and things like that. So it looks all nice and it disappears from your plasma, but this doesn't often mean it disappears from your body, but it could be stored in certain tissues, often in your fat tissue. Yeah, but you see, like there are big differences, and yeah, certain drugs like chloroquine and so on, it's basically 10 to 24 days. So it's you can basically detect the things in plasma like for a month afterwards, and have very long half-lives. And also, of course, things are like just appearing in like I don't know, cocaine and so on. It's just basically stored in your hair vessels and so on, because the drugs and medications go in many tissues, and they can be stored and just be some metabolites you can detect forever. Yeah. Area under the curve. I think this is pretty intuitive. You just try to estimate numerically, okay, what is the area under the curve? And you do this now with the, it's called trapezoid rule. Anyway, they just use this trapezoid for all these data points, calculate the area, and then sum up the area. This is pretty easy. But you often find, in addition, is like an extrapolation to infinity. We'll explain in a second what this is. But here's just an example of two curves with basically they have the same AOC, but they have very different curve forms. So you can see there could be a drug which has a fast absorption and fast elimination, and it can have a very similar area under the curve than a drug which has a very slow absorption and a bit slower elimination. This extrapolation until infinity, it basically means you only measured until a certain time point. In our example, for the pretenderlone, it was until 36 hours. And then you can use this straight line and just extrapolate it until it cuts the x-axis. And you can calculate the area of this triangle. And then you could say, okay, if I would have measured forever, until infinity, this is the area I missed because I just stopped after 24 hours sampling or 36 hours sampling. So often we find this AOC until a certain time point, or it's the AOC extrapolated until infinity. Yeah, volume of distribution, like I mentioned, it's a bit of strange concept, but somehow really interesting. So it's basically you put a certain dose in your system, for instance here 100 milligrams of a certain substance, and then you can measure, like in the plasma or in this fluid, you can measure the concentration, and based on the concentration you can calculate a certain volume. So basically, if you put 100 milligrams in here and you would measure 1 milligrams per milliliter, then you can say, oh, my virtual volume is somehow 100 milliliter. Yeah. What can happen, or what can change this volume of distribution, is basically, okay, it can be that your substance is not really the substance basically disappearing. This is often like because it's absorbed and going into tissue. You have certain tissue distribution, or it's bound to proteins. You often have plasma protein binding of drugs, and then it suddenly looks like you have a much lower concentration in the system. This is the so-called free concentration you can measure, but it's basically because a lot of your drug is just absorbed to proteins or is distributed in tissues, and so it looks like this virtual volume is much higher. For a drug which is basically not going into your tissues and doesn't have much protein absorption, this volume is basically your plasma volume of a few liters, so 6 to 8 liters. And you can see this for drugs like warfarin. They are basically just distributing the plasma, not going much into tissues and so on. And so this is often what you see here. For others, you have a very high distribution. Here also, again, the cannabinoids are a good example, where you have like extreme distribution in the fat tissue, and basically everything is going into the fat and the tissues and stays there for a pretty long time. This also that's why you have such a long half-life, because it's basically going everywhere, and then it's has a high affinity to a lot of receptors and the tissues, and then it goes only out like after a long time. So in summary, this is what you normally see in such publication, often such tables with pharmacokinetic parameters, often time courses, sometimes for individuals, most of the time for groups of people. Often you have like strange axes, rhythmic axis, or broken axis, and so on. So you have to be very careful when looking at such data. Okay. So this is basically okay. Giving you basically giving you an overview of what you have to expect if you read such publications. Then back to the variability. I showed a few examples of such drugs, but in reality, it depends a lot on many factors how this actual curves look like, and many things can affect these curves. For instance, here you see two examples. In the first one, you basically have the same peak concentrations, but you have different elimination rates. This is the example I tried to say before, and this is basically showing you if you have a larger elimination rate, this curve goes down faster. And you see this also in the logarithmic plot, basically the slope of this axis, the slope of the decline, which is the elimination rate, is basically faster here for this black curve compared to the orange part. Second example is here you have same elimination rate, and you see this in this parallel lines in the logarithmic plot, but you have very different maximal concentrations at the beginning. And there's often these elimination rates are highly variable between individuals, but also the maximum peak concentrations you reach. And this is because all the processes involved, like absorption, elimination, distribution, and so on, they depend a lot on your individual properties, on body weights, tissue distribution, and your blood flows, but also what proteins you have, and so on. You can basically you don't know much about how these drugs are eliminated. There are some rules based on the physiochemical properties of substances, like hydrophobicity, and okay, how much is this protein binding, and how is it charged, and so on, so that you have some general rules. But overall, you find drugs which are all over the place. So you have like certain drugs which have high volumes of distributions and have a very high clearance, and also basically the opposite. And these pharmacokinetic parameters determine often, okay, what is the possible application for this drug, and also what is the dosing I have to give. Large variability, and you see this for the for instance, if you look at plasma concentrations after you gave a certain dose. Normally you would expect, okay, if you increase the dose, you would also see an increase in the plasma concentration, and for this should lie somewhere on a straight line, or at least on a line. It should be somewhere, but in reality this is basically a large point cloud, and this means for every person this this looks very different, the pharmacokinetic parameters and the distribution and so on. And you see also similar variability here in, okay, what concentration of warfarin is reached, and all these people trying to reach the same dose. So that's basically you take your tablets, you read your prescription, and the doctor tells you should take this, I don't know, once per day, 2 tablets. And then you expect, okay, you're in the therapeutic range, you have the right concentration, and your medication is working. But in reality, it's more like, oh, okay, if you let's say, like, if you're lucky, or like for 50% of the people, you're in the therapeutic range, but for the other things, like you're much too high or much too low. But most of the time it doesn't matter, because you don't have too severe adverse effects, and if the drug doesn't do what it should do, okay, most of the time, okay, this is also not a too big deal. But yeah, it's a bit of guesswork, and this I should take so much drug per body weight is it's more like, okay, it's a rule of thumb. In reality, you have very different concentrations. A big problem in this variability is also adherence patterns. This is I just wanted to mention that because it's an interesting thing, and it's more like, yeah, people say you should take the drugs and you should take it every day, but a lot of patients basically they just stop taking the medication, or they forget it, and they take 2, and so on and so on. So it's very difficult to take your medication every day, especially also for older people and so on. So like this adherence is very bad, and so you often have like a lot of side effects or non-effectiveness of drugs, because people are just not taking the things every day. And there's like I mentioned, a lot of factors can influence it. Just if you take a tablet after you eat or before you eat, things like that. So the ideal thing is to do this as every day the same, let's say like that. Don't do too much crazy stuff if you take medication. A good example is here also for the therapy with an antihypertensive drug. I'm not sure if this was, I think it was ramipril, but I'm pretty sure the same applies also for lisinopril. It's more like showing how basically the fall of adherence in treatment. And you can basically see people start pretty optimistic on day 0, over 95% take their medication. But if you look over a year, this falls basically down to almost 50%. And it's lots of people know that they should take a lot of medication, but then at a certain point, okay, they forgot it once and twice, and then they just stop taking the medication. And this is what we're seeing a lot also in hypertensive medication. Yeah, for older people, this is really difficult if you're already a bit impaired and you have like a whole cocktail of medication you have to take every day. Like without a pill box, somebody's filling for you. This becomes really difficult to take medication properly. Part of the variability in this response is definitely due to the large variability in enzymes. So a lot of enzymes are involved in the pharmacokinetics and drug metabolism. One example are the cytochrome P450. And this is a class of enzymes which metabolize a lot of drugs. And if you here look just at the enzyme abundance, so how much enzyme you have in the liver. Every dot is basically one patient. You see a very large variability in the enzyme. It means more like, okay, if you look at different people, they have very different amounts of proteins. And of course, it makes sense if the protein is converting your drugs and is responsible for the metabolization. The more you have, the faster you eliminate and so on. So if you have a large variability in just your enzymes and the enzyme amounts, then we can expect also large variability in the pharmacokinetics. And we see this throughout the different isoforms of these enzymes and the different enzymes which are involved in the drug metabolization. So you often have this cytochrome P450s, which is a first phase of drug elimination. And it's basically just a conversion or modification of the drug. And then you often have the second phase of modification, which is via the UGTs, and also there you see a pretty large variability. So variability in pharmacokinetics is due to this changes in protein amounts. The second factor, which is often discussed in the literature, and it's definitely true for certain enzymes and certain drugs, is pharmacogenomics. And it basically means you have different variants of the enzymes involved in drug metabolism. And depending if on the variant you got, you have to thank your parents for that. You have different elimination. So you can have like variants which have perhaps up here. You can have variants which can metabolize drugs very fast. Then you're an extensive metabolizer, and you get low area under the curves and pretty fast elimination rates. Or you are a slow metabolizer which can't metabolize much. Then you get much higher areas under the curves and like a slower elimination. And you can see that a lot of this variability in this curve is due to the different variants. In addition, you can have different number of copies. So for the CYP2D6 is this variant is definitely the poster child for this pharmacogenomics. There you can even have multiple copies of the gene, and so you can imagine that if you have multiple copies from a gene which is highly active, basically an extensive variant, then you have like very small area under the curves and very fast elimination of the drugs. Okay, and this definitely explains also part of the variability. We have the different amounts of the proteins times the different genetic variants, times the variability which we have just in our body composition, and then you see a large variability in the drug elimination. So how do we handle such data? What we developed is database for pharmacokinetics data, and this is basically like I would say one puzzle piece in building these models. So we on the one hand we're building the computational models and also software for simulating, analyzing these models. But we need also like bring the data to the pharmacokinetic data together with these models. So part of it is like for model calibration, model parameterization, but also in the validation phase. So it's more like model parameterization means you do simulations with your models and compare it to actual data, and then you use this difference between simulations and data to adjust the parameters in the model so that the agreement between model predictions and your model gets better. Yeah, validation is more you didn't use the data for model parameterization, but it's more like you do model predictions with your model and then use the data set and compare it to the actual model predictions. But for both, you need the data in some standardized format so that it gets easy to bring the data together with the model, either to compare, basically to compare it. And for the pharmacokinetic data, we built basically this PKDV database, which is a database where we store this time course data showed, but also the pharmacokinetic parameters, plus additional patient information and information about the interventions. That makes it easy to bring this together with the computational models. And so part of the model building process is like basically getting data out of applications for model calibration and validation, putting it into the database, and then using this data for actual simulation. And so part of your project is basically you have to read a publication, understand what is in there, what is the pharmacokinetic data and parameters, and then put it into a format that we can use it together with our computational model. How this looks normally, this is now like not pretend alone anymore, but this is from a real study. In this case, they studied the pharmacokinetics of caffeine in different subgroups, in males and females not taking oral contraceptives, and females which took oral contraceptives. Then you can see here, okay, on a logarithmic scale, they reported the concentration of caffeine over time for these different subgroups, and then calculated for the 3 subgroups this pharmacokinetic parameters. So this looks already pretty similar to what I showed before. And then you have a lot of information also in the text, and this information is mainly information about the groups. So what were the subgroups here, like 13 males, which had a certain age range, a certain body weight range. What was this oral contraceptive groups of the females? What oral contraceptive did they take? Were there smokers included? Did they take other drugs and so on? So there's a lot of additional information, which is important to understand where the variability and the differences between these groups are coming from. Yeah, and so bringing all this together, so live demonstration. Not sure this works. Yeah, that is probably not working. Yeah, part of this is basically this database, and then we have data for the different studies. Oh, I probably will say will show. So we have a different instance of this database for this XResearch project, and there's only the subset of the ramipril data in there at the moment. So you can see like in the first project we created around 17 studies, and then you can see for the certain studies, okay, what data was reported. And this data consists basically of the general study information. Okay, in this case, what was it? Ahmed Atta, he created this data set, and there was in the end one group of humans, which were all healthy, and certain things were done. In this case, they gave 2 different doses of ramipril, and then there were different time courses reported for the pharmacokinetic time courses recorded. And so basically the idea is to get the lisinopril data, which we need for the model, in a similar format, and put it into the database. So this is part of the contribution you do. The other part of the contribution is that you have to simulate your actual data and compare it. Like basically, you have to use the model and do simulations with the model of your interventions. And in such a case here, you have to simulate, okay, what would happen if I give 10 milligrams of ramipril, or in your case then lisinopril, and then compare how the model would predict this data. Yeah, and what you can do in the end with such a database, of course, you can do a lot of data integration. And you can imagine, like, if you have data from multiple publications, you can look at certain effectors and see where the variability is coming from. We did this, for example, here for the caffeine clearance, and looked at the smokers in blue and the oral contraceptives users in orange. And we basically can see that smoking and oral contraceptive use had a strong effect on caffeine clearance. And so in the end, this means like this means somehow, okay, if you're smoking, you can drink basically more coffee because in the end, it results in an induction of the CYP1A2 enzyme, which is responsible for the caffeine clearance. And so like the more you smoke, the faster you clear the coffee. And so on the other hand, if you take oral contraceptives, as a woman, then often or you see an inhibition of this CYP1A2 enzyme, and you clear caffeine much slower. So meaning, okay, like basically, if you suddenly start smoking or smoke a cigarette, then on the next days you have a very different clearance of these drugs. And this is very interesting because it's often like for the smoking effect, especially a single cigarette, you can see already these inductions after 1 or 2 days. And this is for many I'm not sure if smoking is a lifestyle factor, but for many, let's say lifestyle choices, it's basically what food you eat, what how much sport you do, what medication you take. It affects directly this enzyme distribution you have, and it directly affects also like the clearance of medications. So for instance, things like there's a ton of things which can affect, like for instance, the CYP1A2. Like this is if you eat too much broccoli, if you eat too much smoked meat, and I don't know, like a ton of things affect that. And it's very interesting because the different you saw this many isoforms, they are affected all differently by this different lifestyle factors. So like here for this drug, it could mean if you take oral contraceptives, you clear caffeine worse than if you wouldn't take the drug. But for other medications, it could mean exactly the opposite. And so this is like where you often have like this drug interactions, or I would say it often also food drug interactions. A good example is a grapefruit juice, which has a ton of interactions. So basically, I would say don't drink grapefruit juice. If you take medication, it's more likely than not that there will be some drug interactions between grapefruit juice and any medications. Especially also for this, what's it called? The the antidepressives and so on. They have a ton of drug interactions, and that's often what people also like. Or depression medication, it's often affected a lot by lifestyle choices, and so you have these interactions which are often non-intuitive. And yeah, this is also like yeah, I think people are not aware, but like here you can see also like smoking, and this has really large effects on the actual clearance. And yeah. Okay. Yeah, no, let's see. Okay, I'm a bit faster than I expected, but it's good. Then we can do a bit more. Yeah, I wanted to do some organizatorical things. I would say, please, if you have questions, just ask until here. Otherwise, I would make now a bit of shift in topics. Okay. Okay, the one thing which we have to do is that you have to do a bit of data camp courses. I think the two things you really have to know for the course is, on the one hand, a bit how to work with Git and GitHub, because you will contribute your contributions to the project via Git and this version control. So you have to have a basic understanding how to do that and how this works. The other thing is, okay, the more Python you know, the easier it is, and the more you can contribute to the project. I would say that like that. Yeah, even if you don't know much about programming and much about Python, you can basically do your things, but it gets easier the more you background knowledge you have, and it's also you can take more away from the course. So one thing we will do is I would say we're doing this interactive data camp courses. So I assigned you to two courses. The one is like this GitHub concepts, and the other is the Python fundamentals. This shouldn't take too long. I did today the GitHub course to see if this makes sense, and I think it's like 2 or 3 hours or so. Probably if you do the video in two times speed, you can do it in 1.5 hours and so on. But it's also like it gives you the basic concepts, and you don't need 100% of what you learn, but I would say most of it is really helpful for the course. The other one is this Python fundamentals, and it gives you some basic introduction to Python. Same here, like if you have a lot of knowledge about GitHub and Python, I bet you can select a different course, just talk to me. But I think it would be good if everybody is doing one assignment, and this takes a few hours, and you have a few weeks to complement that, to complete that. Exactly, and it's a bit of interactive. Most of the time, it's a bit of videos, and you have a bit of questions and so on. I found this pretty intuitive. Sometimes the questions are not very straightforward, but it's okay. If you watch the videos and take in the materials, then it's pretty easy to just complete the course. The second thing is that we have to work on GitHub together. And we do this via this repository, this XResearch2023 repository. And I would need, you all need like basically access to the repository, and I can only give you access if you send me your GitHub account. And this is where we contribute all our information. And what I need basically first that you become part of the project, and then you can start contributing. And one of the first things you have to contribute is basically your own author information, that you would add basically a file with your information, so that we can add you to the author list and to the people who contributed list. So this would be one thing. And then when you reading your paper and working on the pharmacokinetic data, you would add this also in a subfolder, and basically work on one study where you responsible for the data. And then you would create certain data assets here. Like, for instance, this is for this Ramipil vein bridge study. Yeah. So how you normally interact with that? What you have is a GitHub client. So there are two ways to interact with that. The one way is if you're more a computer, I don't know, computer literate, and like know what a console is and know about the programming, you can basically do this interactively via a console and the git command. So normally you have this project, and then you can via this git commands just interact with this environment, and then you can do things like pulling changes and committing changes and so on. So this is the one way to do it. Most of you probably have no clue what I just demonstrated. No worries. There's also an interactive, basically a graphical front end, which is called GitHub Desktop. And this provides an abstraction layer around this commands, and you can just click on certain things, and then it should do what you do. And this is basically called GitHub Desktop. Let's see if I can get this starting. And so here you would you basically just say, I want to add this repository, and then you can easily manage your file changes and upload them. And also get the file changes from the others, because you can imagine this is one of the big why we're using this Git and GitHub and version control is basically because suddenly we are 10, 12, 15 people working on the same projects on different files, sometimes even on the same files, and we have to bring everything together and manage that. And so that everybody can work at the same time, and we're not destroying all the files at the same time. And so this is basically the layer you would probably use, and then you would make changes to the files, commit the files, and then update them. But for that, it's good to go do this data camp introduction about this GitHub fundamentals, get access to the GitHub repository, and probably also just try to get this GitHub desktop set up, and that you can get the files locally on your computer. Yeah. And how this works, and basically you have your own computer, and then you have a local copy of this file here, and oh, sorry, I'm not sure you can you still hear me? I probably have to close some stuff here. Okay. Okay, can you still hear me?
Yes, we can.
Perfect. No, before I opened, I should have closed some things before I start the lecture. Okay. Yeah, but what you have here is basically it's a local copy of what you see online here. So give me a second. Basically, you see here, these are my local files, and then if I change something, I can bring the changes back here in the repository. So yeah, for instance, I could here I would just add a dot. So I manipulated the file. I will save the file. And then now I have local changes I did here on my hard disk. And then I want to bring this changes back. And then what I see now here, GitHub desktop, suddenly I see already, okay, it automatically detected this file is changed. It even shows me the changes here. Okay, I added this here. This is my my modification I did here. And then I can do a commit message. This is basically, I'm now telling all of you, okay, what I changed. And here, okay, I just fixed a typo, nothing important. And then I can here commit this to development. Now it's basically nothing commented. I just set all my changes I have, like I gave it a name and I described it. And now I can basically push it. And pushing means my local copy, it's going back to the repository. So I can now click here, push. And then I have everything online. And if other people would now put changes in there, you would say basically get notified here, hey, man, there are changes from other people. Please pull these changes first, get them in your local copy so that you can change these files also. And then if you go back online, you see now basically I did a change here, like just now I fixed a typo, and I can even now see online, okay, what are the files I changed, and so on and so on. And so then we have also some like some provenance, what happened and who did what, and who is responsible for what. And so we can manage that easily here in the system. Exactly. And so in the end, you basically need access to this, and you should probably get this GitHub desktop running locally and do this course and figure out what is GitHub all about, and commit, try even to be commit your author information. And this would basically be just, okay, go to this author, Slisinobril, create a file with your own name, and just put the information in there. Okay, that's not much information. Basically, put your name, university, and you should probably get an ORCID, which is an ID, like where researchers can just basically you can the things you contribute to the research field, they can uniquely be linked to you as an author. So okay, and so you would just create one file of these for your own, and then you could commit it very similar. Then I just changed the file. So this would be like, just give it a try. If it's not working, just ask questions or give me feedback and so on. Okay, this is definitely the one thing. The next thing is we have to decide on this block core states. So in the email I sent today, I suggested some dates. Hopefully this will work for everyone. So you should fill out the form and see what dates work for you best. And then hopefully we'll find some date or some 2 dates which work for most of the people. So this was this block core states. That's basically this. Fill out this form, put in your name, and then we can hopefully one of these weeks will work. If this is really not working at all, we can also do it a bit later. Much earlier doesn't make sense because we have to until the course we basically you have to have this GitHub thing running. You have to have read your paper and should have created the data for your study, so that when we do the course, you can really focus on the model building and the simulation of your papers. So that's why much earlier is not really possible. Later would still be possible, definitely. But also like, it's not good if we don't want to do it in the next, definitely not in the next semester. And the problem is also then people want to go on holidays, so much later is also like it's always difficult to find some date. Let's see how the poll turns out. And last year at least we found some way. And no worries if you can't make all 5 days. If you can do 4 or so, it's also okay. Just select the dates which fit best for you. If you miss a day, you can do the day afterwards and so on. But it should be at least 80% of the time you should be available somehow during the week. The course would be from 10 to 5. Officially it's until 6, but we 10 to 5 when we finished. So it's so if you have this time during the week, then please select the dates. Yeah, I would say we still have a bit of time. Are there any questions until here? Or so I would say in summary, start with this GitHub concepts on the data camp. Send me really your GitHub information if you haven't done yet, and try to do this GitHub desktop and play a bit with a GitHub, and you can make an own project and just check how this works and try to get these files locally via this GitHub desktop. Yeah. Okay, if there are no questions, then okay, first thing now, we basically have to, okay, we know approximately what we want to do. And this is, we want to build this physiological-based pharmacokinetic model of lisinopril. But what we don't have right now is any data about lisinopril. We don't have any clue if this is taking 1 hour, has a 1 hour half-life or 24 hours. We don't know how large the variability is. We don't know anything about the pathways and so on. So we really have to go now in the scientific literature and figure out, okay, what did the people do in the last 30 years with the lisinopril, and where are important data sets which are useful for building a computational model. So this is often the first step in such a project. You have a new research question, you know approximately what you want to do. You build the scope of your research project, and now you have to figure out what is the state of the art and what is the available data like to build a model and to work with that. And so we did this a bit more systematically over the years, and what we do now is basically we're doing a systematic literature research and manage all that via Zotero. And what we do for that is we basically have a Zotero library where we manage the literature, and there basically having the publications about what is important and what is not important. And And then we try to get all the PDFs for that. And then we have to look in the PDFs and do some screening phase and see, okay, is this a paper which is useful for the publication? And so most of this, I would say, most of the screening and literature thing, I unfortunately I have to do that. But it's more like, okay, I have to go through a lot of these things and then have like a top list of, okay, these are probably the 40 papers and so on. We should have a look at, and then you can select one. Because of course, for you, it's difficult right now, like to understand, is this a good paper? Is this relevant for the model and so on? So more like, I will show this general way, like how this works and how we evaluate such publications. And that you understand where the publication you select or get is coming from. And so often this paper look like this here. You have like, okay, you always have a title, effect of here, effect of oral semaglutide on the pharmacokinetics of lisinopril. So this could be something which could be relevant for the model because there is somehow a pharmacokinetics of lisinopril in here. It's in healthy subjects, which is good because we basically want to build a model for healthy subjects and then apply it probably to different subsets, like most likely the hypertensive population, but probably also a subgroup of renal impairment or cardiac impairment, because these are the subgroups which normally take the hypertensive medication. Okay, so, and then you have normally I'm just screening over that to get a quick feeling of the via the figures. Here you see basically, okay, they're showing a dosing protocol that was pretty complicated. They took a ton of drugs. So, and at some point they hopefully reported something. Okay, often you get a table with a patient demographic. This is just telling you, okay, we had 2 different trials, 52 and 32 subjects. Let's see if I can get this a bit bigger. And then you get such curves, and already like hopefully you should be pretty familiar from this here. And then you can see certain things, and here you can see basically, okay, this is plasma lisinopril concentration, and you see, okay, we have 3 groups, and this is probably lisinopril and lisinopril with the 2 different interventions. Unfortunately, this is geometric mean plasma concentration. We never like geometric means so much, but it's okay. And then you see similar things here for the warfarin and the digoxin, which are 2 different drugs. Okay, but overall, and here in addition for the metformin, so overall this looks pretty good. Because you see here we have the plasma lisinopril concentration. This is also interesting because this is basically the first curve I see of the lisinopril plasma concentration, and we can already see, okay, this looks pretty similar to what we saw before. This is oral administration. We see like basically there's different core administered drugs don't have too large effects, and we see like peak concentrations around 10 hours. And we see pretty long half-lives. Okay, if we go here from the 10 hours peak, Tmax, to half the concentration, like from, I don't know, around 60 to something 30 here, we see this is around 10 hours half-life. And another 10 hours we would half again, and so on and so on. So not too fast. It's definitely surprising that this takes so long to reach the peak plasma concentration. You saw for the caffeine, it's like 1-2 hours. So this is probably they're taking tablets which are highly coated or have like very slow distribution of the substance. So okay, but overall, this looks okay. What I don't like is I don't see any error bars, so we have no clue. Like okay. We have no clue if the error bars are basically super big or super small. So nothing about variability here. But overall, I like that the curves look pretty nice and also don't look too crazy if you give different co-medications. So this is, I would say, my first look at lisinopril is pretty good. Here you see, the symbols you should be now familiar with. You see the AUC until infinity, a Cmax concentration. And what they did here, they basically compared, okay, if I give the drug without the other drug and with the other drug, what is the effect? And is the change in this pharmacokinetic parameters significant? And this is normally how you evaluate also drug-drug interactions. If you don't see if you see an effect on the pharmacokinetic parameters between 0.8, below 0.8 or above 1.25, then you would say I have a drug-drug interaction here. I'm not sure. Can you still hear me?
Yeah, we can hear you.
Okay, because now everything is freezing here. Let's see. Oh, give me a second. Okay. I definitely have to close some stuff. Okay. Okay. And then, okay. But this looks pretty okay. And you can see you basically have like also some pharmacokinetic parameters. They are not really mentioned in a table, which is a bit, here this is not so nice. But you see here steady state concentrations, area under the curve until 24 hours, median Tmax. So this should be all sound now familiar to you. And this is basically, okay, I just selected randomly a paper and you can see, okay, this is basically how this looks. There's a lot of difference in the protocol, what drugs you give, what population you have, but the reported data is often very similar. It's patient information, it's pharmacokinetic time courses, and it's pharmacokinetic parameters. So this was this BACTA study. So normally what we do, okay, we do some literature research to put a lot of this publications here in, together, and then we try to evaluate it, and then we normally do this via giving certain tags. So normally I have to, okay, I basically now checked the study, so I give this tag that I checked. I know that it was in human, which is important because a lot of the reported data is for rats and it's like for certain drugs you can find a ton of things in horses and in cows. So basically, if you can use it to like to cheat in horse racing, then it's like studied very well, the drug in the horses. And if you can use it to improve like something in cows or pigs, then it's also used. There's a lot of pharmacokinetic data in these animals. But otherwise, rat is normally the other species you find a lot. Mouse, the problem is they are just too small, and they're in mice the main problem is the repeated plasma sampling. And you can imagine like for yours to determine the pharmacokinetic the concentrations of your substances, you have to sample the blood repeatedly at the different time points, and you just need a certain amount of blood to do your assays. Like it is a problem with I don't know what's this company Theranostics or this company which tried like to sell for billions of dollars the minimal fluidic drug assays and yeah, it's basically impossible to do in very small volumes accurate analytics, and so normally you need like 30 microliter or so of blood for pharmacokinetic measurement. And you can imagine if you only have like a milliliter of blood or like less than a milliliter of blood in a mouse. If you take every 10 minutes a lot of blood out, then basically the blood just the mouse just doesn't have enough blood. And that's why you normally go to rats. They like basically five mice or so. They're pretty big, and they have also like 5 to 10 times the blood volume than a small mouse. And so you can do much better pharmacokinetics. And they're also cheap compared to if you go to, normally you would like to do this in mini pigs or dogs, but these are really expensive, and it's also like not so ethically, and they're basically very expensive because okay, a lot of issues, but this is not relevant for our course. Okay, but so often you find rat data and you find human data and you find horse data, which is like very surprising. Okay, And then we annotate this here. This is species human, and then we would also annotate what kind of data we found. In this case, we found pharmacokinetics data, and I found data time course data. So this is I would say, a pretty good study, and this would be something which is yeah, this is. Sorry, you can't probably see this. I would put this in more in the priority high category. So this is something, there's definitely useful data in there. It's like, let's say, it would be nice if there are, but I don't like, you don't have error bars. I don't like that you don't have pharmacokinetic parameters. I don't like that you have don't have error bars, and a ton of drugs which were given at the same time. So that's it's more like, okay, if there's nothing better, this is definitely something which we will use, but it's more like different things we have to look at. Yeah, this sounds often from the title, you can already see if this publications are useful or not. And like here as a second example, yeah, you can see lisinopril pharmacokinetics sounds what we want. You have a certain subgroup. Here's like chronic renal failure, and once again, scrolling through the publication, if you see such equations, this looks a lot like pharmacodynamics. Often you have this pharmacodynamics, like basically, when do you have the maximal effect? This like pharmacodynamics was more like you're interested in the dose-dependent effect of the drug, and so you often have equations which depend on a maximal effect and half maximal effect and IC50s and so on. So this looks like a pharmacodynamic equation. So just from scrolling over it, they probably did some pharmacodynamics. Yeah, then here in this case, you see a lot of, okay, perhaps I can rotate that. Yeah, here you see data, and you can see individual patient data, which is very nice. And here you see pharmacodynamic data, which is very nice. We see the lisinopril. We see the blood pressure, which is something which we're interested in. And in addition, you see certain things like kidney function, which is measured via creatinine, and also ions, which are important often for the blood pressure regulation. Okay, so this looks pretty good. But you see here, you see now lisinopril concentration. Now it's in serum and not plasma. And you see this is over very long time periods. Before you saw this nice peak, which is going up and going down. You can now imagine if you only sample like every 24 hours, you're not getting this nice wave-like structure, which I basically showed on one of the first slides. Something, but basically, of this wave, you just take a single point. And so normally there would be these bumps in here in the concentration. We just don't see them because they didn't sample there. And so this curve looks a bit different, but you can see, okay, they got pretty stable plasma concentrations, and there are and you can see this in two different subgroups, and the subgroups were probably somehow different. Yeah, this is also very nice data. You can see steady state concentrations which are reached of this drug after certain kidney function. And so this would be really important data for the model because it gives us some dependency on of the kidney function on the steady state plasma concentration. Okay, so this would be interesting. And otherwise, okay. And this would be also an interesting subgroup because renal, like I said, the subgroups we're interested in the end is hypertensive and probably renal impairment and cardiac impairment. So this is definitely an interesting paper. You saw they didn't report this classical pharmacokinetics. It's not like we have this nice time courses and calculated pharmacokinetic parameters, but it's more like, okay, they gave the drug multiple times and they sampled it. So somehow there's a pharmacokinetic, but it's not this nice, okay, 36-hour curve, which is going up and down. But it's more like they use this data to then calculate things and correlate it with other clinical parameters and so on. So this is often, it's basically there. The second step, like you have these classical papers, which I showed. The first one was more, and then you have like this more like using pharmacokinetics to study certain pharmacodynamic things or like certain dependencies in certain subgroups. And this is a good example of a second paper. So here also, I would just so this is definitely something we use for modeling. So we have like some pharmacodynamics because we had the blood pressure, and we have some pharmacokinetics in here. We have time courses, and this was all in humans. And so I just tag this as a priority high. Okay. So, but this is basically what I will do, going over the studies and selecting some, and then you basically see only the ones which are pretty good and pretty useful for the model. And it is more like this first evaluation phase that I have to go through the literature and see, okay, what can we use? So now the question, where did this selection of publications come from? And there are basically two ways to search for them. The first thing was via PubMed. PubMed is a large literature database of, no, I would say mainly biochemical research, but definitely not limited to that. But it's, I would say, one of the largest databases for biochemical literature. And then you can do literature searches here, and then use this information and import it in Zotero. And so what I did as a search of pharmacokinetics, lisinopril. So did something like this and did a search, and this gives you already like a first good feeling. So what I look normally at, like and this is basically what you do in a research project. You do at some point a literature research, and you should somehow document what you did and try to systematically evaluate the literature. The first interesting part is like this plot here, and this basically it basically tells you when the drug came on the market. So before 1985, nobody ever looked at lisinopril because probably the drug was not there yet. They didn't have ACE inhibitors, so it's basically our parents, okay, when they were young, there was no ACE inhibitor on the market, or it was probably just in the labs in the rat animals. And around 1985, this was coming on the market, and we can still see there's still some actual research. So there's it's not like that they just. What you often also see, okay, 10 years later, there are basically no publications anymore, and that's often because the drug is away from the market, nobody's interested in it anymore, and there's some better medication and so on. For lisinopril, this looks pretty flat, and which means, okay, there's still interest, and makes also sense because it's like one of the most prescribed medications which we have for hypertension. Also, like the amount of results, it's also like what you can see here. This is one of the most prescribed drugs, but it's not crazy much information which we have about the pharmacokinetics. So there's around 200 papers via the simple search, and many of them are just nonsense and not really related to lisinopril. So there's not, in the end, not too much publications. I can imagine like there's probably 50, 40 which are interesting, and then half of them are high priority. And then you can already imagine, like in our group of 15 people, we can basically do all important papers, like basically we can build a database of all the important pharmacokinetic information which is available for the drug, and be pretty comprehensive about what is there. Like for other drugs, it's just not possible because it's just there's too much going on. If you look at things like aspirin and so on, you can basically see, okay, like we would never be able to evaluate all this almost 2,000 publications. But lisinopril is basically it's a very nice drug and scope. And so what I did to get this into Zotero, especially in the end, I just clicked here on save. Save all results. I wanted basically PubMed format, and then I just downloaded that, and then I can use this file to import it back into this project. I did this some time back, so I have to redo this and see, okay, what additional literature came in there. And yeah, strangely, there are a lot more publications back then, but it can also be how this search algorithm is changing over time. So you always have to document what is going on. But in the end, okay, we are around 200, 300 papers which we can get out of this here. Part of the work is then to getting the PDFs. It's the next step. Often you have access via the universities, so we basically retrieve this automatically, the PDFs, or otherwise we try via different methods to get access to the PDFs. Okay, second, okay, I need 5 more minutes and I'm finished. So second part which we have is this Pika PD AI, and this is it's a database which allows also to search for such literature. It's basically they went over the literature and searched for it, and you can then search for certain substances here, which is pretty good. But I have to say most of the results are very, very similar what we find with the PubMed search. And so we basically do the search and then export the results, and we can see, okay, here we get like this nice relevance score, and we can see a lot of these look like very interesting, and we will probably have like nice pharmacokinetic data in these. But the overlap between the PubMed search and this is pretty high. And so what I did also, I imported the results from this here, and then I removed the duplicates from these two searches. And then in the end, we basically have such a database which, okay, somehow the numbers are not, I don't know what's going on here. Yeah, but we basically, you can see we have 241 items, and basically all of these items from this database, from this search, are also appearing in the PubMed search. I think so far so good. So the main task until next week is I will go through this database and find the top publications, and then we will start doing basically a table with this information. So this is from the Ramipril. So it's more like the US students and me are getting assigned certain publications, and then you have to check, okay, what is the information which is available in this data set, and you have to then over the next few weeks start to get the data and information out of this publication, so that we can build a knowledge base of what is lisinopril. So that's basically a knowledge database that we know what is the scope, and from that also we get the actual research question. Okay, what subpopulations do we want to look at? Do we have sufficient data for renal insufficiency? Do we have data for cardiac impairment? Or like often like the interesting questions come by just looking at the literature and looking at the actual data, because you see, man, they're really interested, or like in many paper we see this and this mentioned. Okay, how is the interaction with that? And or in elderly we have this and this problems. And then the questions for the computational models arise basically from this data and knowledge. And our problem is basically we're like naive people who never heard anything about lisinopril, and we now have to get like basically the last 30 years or 40 years of research we have to accumulate to somehow get the knowledge base for building a model and doing something novel based on the existing literature. And I think here's also what these computational models can really contribute to the field, because they can be really knowledge integration and integrate many different puzzle pieces together to then provide new answers or translate to new questions which we couldn't answer from the data alone. Okay, so far so good. I would say the main tasks are get this GitHub running, look at this data camp, And then we would start the assignment for the publications. And please fill out this form for the course so that we hopefully next week can decide on the dates for this blog course. Okay. So if you have any questions, please ask. Otherwise, I will share the slides and the information. Also, feel free to ask questions in the chat or in the in Slack or via email. Yeah, thanks a lot. And
yeah, thank you. Bye.
Thank you, Matthias. Bye.
Thank you.
Bye.
Bye.
Thanks. Bye.